Okay, Highlanders, it's time to talk about max and min. So remember the concept here with your maximum and minimum values, and we're talking about relative max and min. So for example, if you have a function that happens to look like this, some sort of polynomial function where we have two relative maximums and then one relative minimum. And the key here, as we've talked about many times, is those tangent lines at your max and mins are all horizontal, which means that your derivatives are going to be zero at those points. So keep in mind that this critical point here, this critical point here, and this critical point here are the x-coordinates of the relative maximums and minimums. The actual max and mins are the heights of those functions at those particular x values. So the idea is we need to find the zeros of the derivative function, because the zeros of the derivative function are going to give me the locations of those max and mins. So, and that's really the whole idea here, and it's all we're doing in this week is max min. So you're going to get this example that has just functions, and then you're going to get some story problems that you need to work on that's going to involve some geometry. So we'll start with this example first. I have a function here, and so since I'm looking for the relative max and mins of f, I need to find the derivative. So it's straight up power rule. So that gets me 12x cubed, 4 times 3, drop the power 1, 3 times 4, drop the power 1, and this, I'm sorry, this should be 24. So then 2 times 24 is 48x, and we drop the power 1, and then minus 48. So that is the derivative function. And then what we need to do is to take our derivative function and set it equal to 0, so that we can find the places where the tangent line is horizontal. Okay, so now it's a question of solving this polynomial, and we notice that every single one of these coefficients is a multiple of 12, so I'm just going to divide everything by 12 to make it easier. So we have x cubed plus x squared minus 4x minus 4, and then we have to summon our algebraic powers, and what we see is this can be factored. Since it's a 4-term polynomial, we're going to group, taking care of our negative sign. I'm going to factor out the x squared, leaving me x plus 1. I'm going to factor out the minus 4, leaving me an x plus 1. And then factoring out the x plus 1 leaves me the x squared minus 4. And then continuing, so we see that my zeros are negative 1, negative 2, and 2. So again, these, remember, are the zeros of the derivative function. So these are the places where the function, or the points where the function has a slope of 0, which is going to be at my max and min. So what we see now, if we're going to identify, and again, we got to go back to our original function f, and this is a 4th degree function. So if we were to take a look at the graph, we know what the end behavior is. This is going to go up in both directions because the leading coefficient is positive, the degree is even, and we have at negative 1 and at negative 2 and at positive 2 is where we have derivatives. So this, derivatives that are 0, so this is going to have to be a minimum. So at some point we minimize here, and then at negative 1 we're going to maximize, And then at 2, we're going to minimize again because we know the graph. So this is the graph of f. And what we see at 2 is where we have a minimum, at -1 a max, and at -2 a minimum. So this, knowing what the end behavior of the particular function is, will determine what you have, so that when you go back and you say, okay, I've got 2 relative minimums. So if I say I have a relative minimum at -2 and 2, and I have a relative maximum at -1. So to be able to find these y values, I'm looking for the actual y values at those points. So then I have to plug these values back into the original function f. So this would be whatever f of -2 is, whatever f of 2 is, and whatever f of -1 is. So these are the actual mins and maxes, because remember, your mins and maxes are y values. So one more time, you would take this, plug it into the original function. If you were to plug this back into the derivative function, you would get 0, which is what you should get, right? So remember, these are the critical points. They're the locations of the max and mins. And also, remember what happens at a max and a min. We go from decreasing to increasing to decreasing and back to increasing again. So this also tells me where the function's increasing and decreasing. Okay? So you're going to have some problems where you're just doing that. You're just finding those max and mins. Okay, on to some story problems. So the first one is we are looking at 2 numbers whose sum is 55, but their product is the largest. And so within the story problem, the first thing you want to figure out is, what am I maximizing or what am I minimizing? In this case, we're looking for the largest product of 2 numbers. Now, I don't know what those 2 numbers are, so I'm just going to call them x and y. So that's number 1 and number 2. And then I'm going to write the equation, because in all of these story problems that you're going to be working on, we are going to be needing a couple of equations here. And whether those are formulas in geometry or distance formulas or whatever it is, in this case, we're just looking at equations. So we're trying to maximize the product of those 2 numbers. So this is my objective. I want to maximize product. Okay. Now, because we have these 2, we need to turn p into a function of x or y. Doesn't really matter. So this is where the constraint comes from. We need those 2 numbers to have a sum that is 55. Or in other words, my second equation has to add up, the 2 numbers have to add up to 55. Excuse me. So, this is where we're thinking about this as a system, and I need to get rid of one of these 2 variables, and like I said a minute ago, it does not matter which. So I'm going to go ahead and solve for y in terms of x, and then I'm going to take this and replace the y in the product equation with what it is equal to. So now what we have is a function, or the product as a function of x. So it's x times y, which is 55 minus x. Now, at this point, again, we're looking for the maximum value of this function. So that means derivative, and that means set it equal to 0. So the idea here is we need to find the derivative of p. And since this is a product, you can use the product rule. You can distribute the x and just do straight up power rule. However you wish to differentiate this is up to you. I'm just going to show you how to find the derivative here using the product rule. So remember, the product rule is the derivative of the first function times the second plus the first function times the derivative of the second, which is just -1. And again, we wish to set our derivative equal to 0. So I have negative x minus x is a negative 2x, and that's plus 55. So that means 2x is equal to 55. So dividing by 2, x has to be 55 over 2 is one of the numbers. So the other number, which is y, is going to be 55 minus 55 over 2. So again, that's also 55 over 2. So those are my two numbers, which again would make sense in this case because if you take half of 55 and square it, you're going to get the largest product, or would be the largest area of the square. But again, not always the case when we're working with this, because this was just adding the two numbers together. You know, you can change this problem by changing and saying maybe twice the first number plus the second number is 55, and now it's no longer a square, it's a rectangle with many options. So that's how this works out. But again, keep in mind, first thing you want to do, what are we trying to maximize? Write that equation. Go back into the story problem, find a second equation, a second relationship between those two numbers. Treat it like a system, solve for x or y, plug it in, and then it's just a matter of finding the derivative, setting the derivative equal to 0, and solving. Okay. Example 3. These are going to get more fun as we roll along. So now a real good application here. We are a large soup company. We are a big, like Campbell's, and we are manufacturing soup, and we need the soup to contain 64 cubic inches, and so we're making a can, which is in this case a cylinder, and we want to minimize the surface area of the can, and we would want to do that because then that minimizes our cost. So the idea is, you know, if we can still put in 64 cubic inches of soup, but we, you know, into the smallest container possible, will allow us then to, you know, not use as much material, which is going to minimize our cost in production. So this is the whole idea here. So what are we trying to minimize? We're trying to minimize the surface area. That's my target. So again, we're looking at a cylinder for my soup can, where this is my radius and this is my height. And so the surface area of the can, we have two bases, so we have 2 pi r squared, and then we take the circumference of the base times the height, and that becomes your lateral area. So this is something that you would have done in geometry back in the day. If you don't remember a formula, obviously look it up, but this becomes what we're trying to minimize. And if you notice, we've got two variables here. We've got an r and an h. Those are my dimensions that I'm looking for. This is what the can has to contain. That's the volume. So this becomes your constraint. So the volume has to equal 64 cubic inches. And to find the volume of the cylinder, we are taking the area of the base and we are stacking it up h high. So the volume is pi r squared h has to equal 64. So here we have our system, just like we did in the previous example. And now we are going to eliminate r or h. And I think what might be best here is to solve for h because it's not a square, right? So this would be the easiest one to solve for. So that's why I'm choosing it. So I solve for h in terms of r, and then I'm going to take this and plug it in. So what that does then is gives me a function for the surface area in terms of r. So it becomes 2 pi r squared plus 2 pi r, and then h is 64 over pi r squared. Cleaning up a little bit. we can eliminate the pi, eliminate 1r. 2 times 64 is 128 over r. And so the easiest thing to do here to find the derivative would make this r with a negative exponent, so we can straight power rule. So we get 128r to the negative 1. Now we're going to go ahead and find the derivative. So s prime of r becomes 4 pi r plus a negative 128 r to the negative 2. And then remember the next step. The next step is to make sure that we are setting this equal to 0. So we're going to go ahead and do that. We're going to set this equal to 0. So 0 equals 4 pi r minus 128 r to the negative 2. And then we're going to go ahead and I'm going to take this to the other side. So I have 128 r r to the negative 2 equals 4 pi r. And I am going to multiply. So I want to get rid of this. I'm going to actually square both sides. I can reduce this because 4 does go into 128. So this becomes 32 r to the negative 2 equals pi r. And then I'm going to go ahead and square both sides. Actually, I am going to check that before I square. I'm not going to square both sides. What I'm going to do is I'm going to isolate this r. So I'm going to divide by pi. So I now have 32r to the negative 2 over pi equals r. And I don't really want to square it because I don't want to make that number, even though I could. What I'm really going to do is I'm going to multiply both sides by r squared. Because this times this is just r to the 0, which we know is 1. So I have r cubed equals 32 over pi, in which case I'm going to take and I'm going to cube root both sides, which means that r is approximately, the old trusty calculator out here, the cube root of 32 over pi. So I'm going to take 32 divided by pi to the 1/3 power, which is about 2.16 or 2.17 if we round. And so that is in inches. And then we just got to go back and find h. And remember, h was 64 over pi times r squared. So my height becomes 64 over pi times my answer squared. So h is about 4.34 inches. So again, those aren't exact, but they're pretty good, depending upon what your machine would actually be able to make here. But a cylinder with a radius of 2.17 inches and a height of 4.34 inches will contain 64 cubic inches of soup, and this will give me the minimum surface area. So again, what did I do? Figured out what I wanted to minimize, write that equation, and then go back and look for the constraint, which is that, and that's a volume, so write that equation, solve for one of the variables, plug it in, then you're on your way. Find the derivative, set it equal to 0, and start solving. Okay, got 2 more examples for you. This next example is, we have a man stranded on an island, finds a rowboat, and he is going to get to shore. He needs to get upstream 4 miles from his closest point as possible. So the idea here is, again, so here's, I'm going to draw you a little picture, because sometimes pictures always help, right? So we got our man, here's his island, he's here, here's your shoreline. He needs to get to this point, which is 4 miles from the closest point. So from the closest point means we go perpendicular to that straight shoreline. And this is 3 miles. And this is 4 miles, which is the closest point on shore. So he wants to get here, but he's got to, this is your water. So he's going to row to the shore and walk the rest of the way. So that means we're probably going to do some rowing to a point, and then we're going to walk. Okay, so he can row at 2 miles per hour, and he can walk at 4 miles per hour. So you might think, well, why didn't he just do this as short as possible and walk the rest of the way, because he walks faster? But what does that do? That increases your distance, right? So obviously you want to try to cut down the distance while you're rowing, so that you can get there faster. So this is his target point. He's got to get to this point, and what we want to know is at what point should he land. So where is this location? So the next thing we need to figure out here is, what are we trying to minimize, right? If you notice, he wants to reach this point as soon as possible, so that's time. We're trying to minimize our time from him to get point A to point B here. Remember that time is equal to distance over rate. So we have rates, and if I'm trying to figure out what time is, I'm going to need some distances. So since I don't know what this stretch of land is here, I'm going to call that x. That's what's missing, which means since this whole thing here is 4, this has to be 4 minus x. So this distance to get from here to here is just that right triangle. We use our Pythagorean theorem, so we have x squared plus 9. So now we know our distances, we know our rates, and we can go ahead and write a time equation. And so my time in terms of x is going to be the distance over the rate rowing. So the distance is over the rate plus the time it takes for him to walk the rest of the way, which is your distance over the rate of walking. So this is the time function. So that is what we need to minimize. So again, we're going to have to find the derivative of t, and then we're going to have to go ahead and set it equal to 0 and solve. So I'm going to rewrite this over here. So I need some more paper. Square root of x squared plus 9 over 2 plus 4 minus x over 4. And so now we start to differentiate this sum. So t prime of x, and what we can take a look at is actually, before we do the derivative here, so ignore that little mark. I'm going to rewrite this so it's a little bit easier before I start. So this becomes 1/2 x squared plus 9 to the 1/2 power plus 1 minus 1/4 x. So I just divided the 4 into here. I wrote this 2 as a half, and then of course we need the power rule, so we're going to do this. So now, taking a look at this guy, we have x squared, so we got a function inside of a function, so this is going to require the use of our chain rule. So now when we go to the derivative, we also have a product here, right? But since that's a constant, watch what happens. So when I take the derivative of 1/2, which is 0, times this, we just get 0, plus 1/2 times the derivative of this particular function. So we're going to chain this, which means I'm going to find the derivative of the outside function, which is 1/2 x squared plus 9 to the negative 1/2 times the derivative of the inside function, which is 2x. So again, 1/2 down in front to the negative 1/2 because we dropped the power 1, and then the derivative of the inside function plus the derivative of this, which is the derivative of 1, which is 0, and then this is just minus 1/4. So now what do we have? Because this has a negative exponent, I'm going to take and shove it in the denominator here, so I have really just 2x over 4, because it's 1/4, times x squared plus 9 to the 1/2 power minus 1/4. So at this point, I'm going to take, now I want to set it equal to 0. Right, so we set our derivative equal to 0. I'm going to take the 1/4 to the other side. And cross multiply. So this is 4. We have the square root of x squared plus 9 equals 4 times 2x. So these 4's cancel. And then we have squaring both sides gets me x squared plus 9 equals 4x squared. Subtract the x squared from both sides. Dividing by 3. Square rooting. So x is obviously plus or minus root 3, but remember, right, x represented a distance, so it's just the positive root 3. So now we know that my answer is root 3 from that shortest point. So it would be root 3 miles from the shortest point, or you could write it as 4 minus root 3 from the end point. So again, recognizing in the problem what it was that we were trying to minimize. In this case, that was time, so we had to come up with a time function. So using our rate times time equals distance relationship, we expressed it in terms of time, which means I had to find all the distances because I knew the rates. So that's where the right triangle came in, and again, you get a lot of right triangles when you're doing max-min problems. So that's something to look out for. So we found the distances and went from there. Okay, last example we're going to do here, before I talk a little bit about what I'm going to assign you, is we wish to find the radius and the height of a right circular cylinder, which is this guy. Notice he's inscribed in the right cone, and the cone has dimensions, so this would be our constraints. So we're trying to find the largest volume of this particular cylinder. So again, largest volume is what we're trying to maximize. So we are going to get our volume equation, because it's a cylinder, that becomes pi r squared h. Okay? So the idea here is, how do we come up with a couple of equations now, because I need something in terms of h. And the answer, again, there's a bunch of different possibilities here, but if we were to take a look at dropping down to this point right there, what we have is this particular plane section is a right triangle, and this height right here is 10 minus h, and we have a relationship here between this triangle and the big right triangle, to where we have a couple similar triangles. So from our geometry days, we know that these are similar because they share that vertex angle, the small one and the big one. So since they share that vertex angle, we have that angle that is congruent, and we got the two right angles in the two triangles. So we have similar triangles by angle. So it's probably, whenever you can have similar triangles, you're going to get simple ratios that allow you to handle things. So again, this is what we're trying to maximize. So because these two triangles are similar, I know that 10 minus h is to r as 10 is to 6. Right? So the height is to the radius, or this base, as the height is to the base in the big triangle. Which means that I can divide both of these by 2. I know that 30 minus 3h has to equal 5r. And again, I am going to, I guess this really doesn't matter here, because both of these have exponents of 1. So whether you solve for h or solve for r is not going to really matter. So since I have this pretty much set up to solve for r, I'm going to do that in terms of h. Let's give me a fraction. Let's go the other way. Doesn't really matter. So I'm going to have 3h equals 30 minus 5r. And then I'm going to divide by 3. So h is equal to 10 minus 5/3 r. And then plug it in. So v now is a function of r, in which case we have pi r squared times h, which is 10 minus 5/3 r. So the next step, find the derivative, set it equal to 0, solve, and you're good to go. And if it were me, I would use the product rule here. If you want to, you can go ahead and just distribute and so forth. If you get a function that is some polynomial or some type of function that you cannot solve algebraically, then feel free to go ahead and use your graphing calculator to find the zeros. But again, one option, like I just said, would be to distribute this. So that's 10 pi r squared minus 5/3 pi r cubed. And then go ahead and find your derivative. Straight up power rule, set it equal to 0, solve, and you're on your way. So this is the process, right? And I keep trying to point this out. Within the story problem, they're going to talk about, are we going to maximize or minimize, and what are we? What is my target? In this case, I want the largest volume of a cylinder. So that tells me I need the formula for the volume of a cylinder. And since it has two variables in it, I need to look for another equation. And that, in this case, you had options. You need to find another way to relate h and r together. You could have used the Pythagorean theorem here, but I chose not to do that, and because that would have given me this whole square root that was involved, which again, you can do it, it will work, but look for similar triangles. If you have a situation where you've got a couple triangles, a big one and a small one, look for those similar triangles, because this was a lot easier and a lot more simple equation in the end to work with. Alright, so what I have given you in this particular lesson is there are 3 worksheets you need to do. You will see 4 worksheets in the video lesson. The second worksheet has all of the worked out solutions, so you can refer to it. So you can take a look at different types of story problems. All of the solutions are going to be there, worked out in my handwriting. You do not have to redo those problems. Okay. The other 3 worksheets that are there, the first one, the one retitled Remote 1, the one entitled Remote 3, and then Remote 4, those are worksheets that you have to do. So you've got 3 different worksheets to do. All 3 of those have the answers with them, but none of the work. So you're going to have to provide the work for me to get credit for this week. And then the final 2 weeks of our semester and school year we're going to spend in Chapter 11. So I will restate these instructions in Google Classroom. So please take some time and view this lesson, because this stuff can be a little tricky, and I think it's important to watch me go through it with you step by step. Alright? Alright, Highlanders, I look forward to seeing you this week. Have a great day.